Hi, I'm Rakesh, and I have recently moved to Uppsala University, and I will be talking about the front-end bottleneck in server processors and what we can do about that. This work was done while I was at University of Edinburgh with Chengjie Huang, Boris Grod, the previous speaker, and Vijay Nagarajan. So let's see what exactly the problem is and where it stems from. So due to their complex functionality, server applications are generally organized as deep software stacks, and this deep stacking results in huge instruction working set sizes, which generally reach in multiple megabytes. And if this was not enough, these working sets are actually increasing. And one example of this trend is the search workload at Google that they showed is increasing at 25% per year. At microarchitecture level, these working sets do not fit in the latency critical component, mainly the L1I, the level 1 instruction cache, and the branch target buffer, BTB. As a result, there are frequent misses, and this is how these misses impact the performance. So for L1I, core tries to reach it to fetch an instruction, which is not there. The instruction has to be brought from last level cache, which requires 30 to 40 cycles. Now, during these cycles, front end has not issued any instruction to the back end, directly impacting performance. Similarly, for BTB, whenever there is a BTB miss, core falls through and execute the sequential instructions. Tens of cycles later, the wrong path is detected in the core, and the core flushes the whole pipeline and starts re-executing, which again hampers performance. So what is the performance opportunity here we are talking about? So this slide shows the potential speed up that can be achieved by eliminating all the L1I and BTB misses for a set of server workloads. The blue portion of each bar is the speed up that can be gained by eliminating L1I misses, and on top of that, if we can eliminate BTB misses as well, we can get on average 45% speed up, whereas in some cases, the overall speed up can be about 87%. So now we will see what are the existing techniques to tackle this problem, and then how Boomerang, our approach, is different from them and how it improves over them. So if the problem is that the working set doesn't fit in L1I and BTB, the obvious solution is to increase their size. But if we increase their size, there is a corresponding increase in latency, which again degrades performance. So this doesn't seem to be a good solution. Another option is to do prefetching. It doesn't impact the size nor the latency of BTB and L1I, but it just predicts what are the instructions that are going to be needed in the future and bring them to these structures before they are really needed. So this seems to be a viable solution because it doesn't really have any negative impact. So let's see what is the state of the art in L1I prefetching. The state of the art is temporal instruction streaming, which operates on the principle of record and replay. So they record the instruction access sequence, in fact, at cache block level, and then they replay that access sequence to prefetch the blocks that will be needed in the future. So let's take an example. So on the right, we have two functions. On the left, we have two functions which span multiple cache blocks, and the dark gray stripe shows the branch instruction in the cache blocks. So as execution goes through these functions, these prefetches record the sequence in which the cache blocks are accessed. And they store this sequence into a metadata history storage. Later, when execution reaches one of these blocks again, front-end checks, have I seen this sequence before? And if it has, it starts accessing blocks from this sequence. This way, when all the blocks are prefetched, the execution can proceed without any misses. So this technique works really well. It provides really good L1I miss coverage. But the problem is the history metadata. It results in hundreds of kilobytes of storage overhead. And another problem is it doesn't solve the BTB miss problem. Pipeline is still flushed whenever there is a BTB miss. Similar solutions has been proposed to eliminate the BTB miss as well, but then again adds more storage, and the overall storage cost goes even higher. Now, confluence is a state-of-the-art technique that makes an interesting observation that we do not need a separate metadata for branch instructions, as branches can be extracted from the L1I blocks that we just prefetched. So this way, Confluence removes the need of redundant metadata and provides both L1I and BTB prefetching. And this is how it works. So in addition to having regular L1I and BTB and LLC, it puts a pre-decoder between LLC and L1I. And whenever the execution reaches one of the cache blocks that has already been stored in the history metadata, core starts prefetching it, and the pre-decoder extracts the branch instructions, save them into the BTB. And the block itself is passed on to the L1I. So this way, using just single metadata structure, it eliminates L1I misses as well as BTB misses. But the storage overhead still remains high because you still need storage to record the access sequence for cache blocks. So let's see how we can get rid of this storage. So the key idea here is, instead of storing this control flow information in a history metadata, why not construct it on the fly? So what do we need to construct it on the fly? What we need to know is where the discontinuities are in the control flow. Because in the absence of discontinuities, the code will be executed sequentially. And the only places where discontinuities can be are the branch instructions. If the branch is not taken, there is no discontinuity. And if the branch is taken, there is a discontinuity. So the BTB actually captures these branch instruction or the potential discontinuity points. And the branch predictor can help to tell whether there is really going to be a discontinuity or not. So just using BTB and branch predictor, we can actually construct the control flow on the fly. And in fact, there is a prefetching technique called fetch directed instruction prefetching, or FDIP, that does exactly the same. They construct the control flow on the fly and do L1I prefetching. And this is how it works. So this technique decouples the core from the branch prediction unit with a fetch target queue or an FTQ. What this FTQ allows is that even though core front end is stuck due to any region, maybe there is a L1I miss or maybe there is a back-end pressure, the branch prediction can still go ahead and keep filling this FTQ. So they run independently now. And what it helps in is that these queue can also be used to find prefetch candidates, as these are the instructions or the cache blocks that will be needed by the core front end to fetch instruction from L1I. So the FTQ helps in running the branch predictor independent of front end and also to discover prefetch candidates. Let's take a working example. So let's say a few of the entries of the queue are already taken and control flow reaches cache block A. The block A is inserted into FTQ, and the prefetcher checks whether this block is there in L1I or not. If it is there, we are good, nothing has to be done more. Meanwhile, FDIP also keeps looking for further discontinuities. When BTB says, okay, there is a branch instruction, it consults branch predictor to check whether the branch is going to be taken or not. So let's say in this case, it says, yes, the branch is going to be taken, and there is going to be a discontinuity in the control flow. We go to check what is the target of this branch and insert that target into this queue. And then prefetcher again checks whether this cache block is there in L1I or not. And if it is not there, it has to be prefetched from LLC. Now, if this block is prefetched before C reaches head of the queue, FDIP can hide all the L1I mislatency. And this is really the key point, to insert the cache blocks into FTQ early enough so that they can be prefetched from LLC before the block reaches head of the queue. And the procedure keeps going, find next discontinuity, say it's a call. We don't even need the branch predictor to predict it because it will always be taken. And insert it into the queue and check whether the corresponding block is in L1I or not. So this way, FDIP is able to construct the control flow on the fly and able to prefetch the cache blocks without any metadata storage overhead. But if this technique existed before the metadata-heavy prefetches, why did people discard it for servers? Well, there were mainly two reasons they came up with. The first was limited branch predictor accuracy. As branch prediction is needed to keep filling the FDQ, If the branches are mispredicted, probably you are going in the wrong path. Whatever you prefetch is going to be useless. And the second reason they gave was the limited BTB capacity, because if the BTB is not able to discover branches, you will always be going sequential and probably miss prefetching opportunities. We debunk these claims and show that even despite limited branch prediction accuracy and limited BTB capacity, FDIP is effective in L1I prefetching. And this is why. Majority of the branches, dynamically executed branches, are conditional branches. And this graph shows how far ahead conditional branches really jump in terms of number of cache blocks. So if we see, more than 90% of branches have their target within 4 cache blocks. And its impact on L1I prefetching will look something like this. So we reach a branch which is actually taken, but the branch predictor mispredicts and falls through. So what happens in this case is FDIP is prefetching few extra cache blocks, and in the other case, when the branch is actually falling through and predictor predicts it's to be taken, FDIP is missing some prefetching opportunities. But because the distance is small, the opportunity lost or over prefetching is really small. And that doesn't really impact the accuracy a lot. So mispredicting conditional branches doesn't really limit the accuracy of L1I coverage for FDIP. So FDIP provides good L1I miscoverage. It doesn't have any storage cost, but it doesn't solve the BTB problem. Even though BTB misses are not critical from instruction prefetching point of view, they are critical because whenever there is a BTB miss and the branch is actually taken, pipeline still needs to be flushed, which hampers performance. And this is what FDIP misses by not tackling this problem. It tackles only the blue portion of the opportunity, but not the red one, which can be as high as 41%. So let's see how we can tackle the complete front-end bottleneck, both L1I and BTB, with a storage-less prefetcher. So the key problem of FDIP is that it doesn't do anything with the BTB problem. And the idea here is, just like you can discover a L1I miss ahead of time, you can discover a BTB miss as well, and then pre-decode the cache block where the branch instruction belongs and fill it into the BTB. So what do we need for that? First of all, we need a way to detect BTB misses. Second, we need to get the block from L1, from cache hierarchy, and pre-decode it to fill the BTB. And this is how Boomerang achieves this functionality. It leverages FDIP for L1I prefetching. And while it is constructing the control flow, it also discovers BTB misses. But discovering BTB misses in a regular instruction-oriented BTB is tough, because if the BTB says, I don't have an entry corresponding to this PC, that could be because of 2 reasons. First, the instruction itself is not a branch instruction, in which case, okay, we should go sequentially. But the other case is due to the capacity. Maybe the instruction is a branch instruction, but there was not enough capacity to put that branch into the BTB. So that's why there is a BTB miss. What we use is a basic block-oriented BTB. So instead of indexing the BTB with the branch address, we index it with the address of the basic block, and where we define basic block as sequence of instruction ending with a branch instruction. So what it means is the target field in the BTB should index the next entry in the BTB. So if we index BTB with the target and we do not have a match in the BTB, we do not find that entry in the BTB, that is a genuine BTB miss. So this is how we are able to detect BTB misses. Next, we have to prefetch that block from cache hierarchy, and we prioritize, and since now there are competing techniques, competing mechanisms that want to access L1I, for example, the demand fetch, the BTB misses, and the L1I prefetchers, we give highest priority to the demand fetch, and then comes the BTB, because if there is a BTB miss, we just can't explore the further control flow. So it has higher priority than the L1I prefetching. And finally, we extract the branches from the prefetched blocks and insert them into the BTB. Let's take a look at a working example. So this is the same scenario. We have a FTQ that decouples branch prediction and the core. And let's say there are few entries which are already occupied, and execution reaches cache block A. Boomerang checks whether there is the corresponding entry in the BTB or not, and let's say it's some is. Now, FDIP at this point will go sequentially because it doesn't know there is a BTB miss or not, and prefetch stuff. But when the BTB miss reaches the core, the pipeline will be flushed and will result in a performance penalty. Boomerang at this point, instead of going sequentially, will get the cache block from anywhere in the cache hierarchy, and it will extract branch instructions from that cache block, and then it will go ahead. Insert the corresponding cache block in the FTQ and check whether this block is in the L1I or not. So this is the main functionality that distinguishes Boomerang from FDIP. Now let's see some evaluation results. So we use a typical configuration, 16-core CMP with 8 MB LLC, 32 kilobyte of instruction cache, 2K entry BTB. And for evaluating, we use some commercial workloads and server workloads. And we evaluate different prefetch configurations. First, we have L1I only prefetchers. And these are next line prefetcher, FDIP, and shift, which is a temporal instruction stream prefetcher. And unified L1I and BTB prefetchers, basically Confluence and Boomerang. And these are the results. So we show the red line shows the result, the performance benefit for Boomerang, and blue lines are for other prefetchers. So the key result here is Boomerang matches the performance of a storage-intensive prefetcher, but doesn't have any storage overhead. If you look at individual benchmarks more closely, there are cases when Boomerang actually outperforms Confluence. And this is mainly because of the way metadata is stored and accessed in Confluence. But there are also cases when Confluence actually outperforms Boomerang, and this happens when there are too many BTB misses and Confluence cannot, and Boomerang can't really run ahead. Also, compared to just L1I only prefetching FDIP, Boomerang is always better than that. And this shows the importance of just prefetching L1I blocks is not really enough. We need to solve the complete problem by prefetching BTB entries as well. So Boomerang provides performance benefits of a storage-intensive prefetcher, but doesn't have any storage overhead. To summarize, front-end bottleneck has been a well-known issue in servers, and there has been a lot of research in this direction. But all of the prefetchers proposed in literature are storage-intensive. We show that, contrary to the conventional wisdom, a storage-free prefetcher can actually work. And FDIP is really the prefetcher that works well for L1I prefetching, but it doesn't solve the BTB problem. We propose Boomerang, which solves the complete problem by attaching a BTB prefetcher to the FDIP. So we deliver a high-performance core front end without any metadata storage overheads. And that's all from my side.